Hey there, pre-calculus. I've got a new video for you. It's the third lesson of 2.4, and it's the second lesson where we explore polynomials that have a degree greater than 2, just meaning that its front runner exponent is bigger than 2. So my intention for this video is to go through 2, 4, 6, 8, and 10. Just go through all the even solutions, and then, hopefully you guys can pick up the rest on the odds and make sense of it. So let's get started. First one we want to talk about is g of x, or I'm just going to use y as a variable. G of x equals x to the fifth minus x. Okay, so I'm going to use some big graph paper. And you guys should too. The little grids aren't going to cut it here. All right, so if you recall, when we saw x to the fifth power that fit sort of like that standard form, x minus hk business, x to the fifth pretty much looked like x to the third, except it was just more pronounced at its curves. Excuse me. Here's the thing. When you add to or subtract from an x to the fifth like this, what it's going to do is it's going to morph the middle, okay? It's not going to change the end behavior. It's still coming from negative infinity, and it's still moving to positive infinity. But what we can predict will happen with this graph is that this is going to morph to look more like this. Because what it has to do is it has to cross the y-axis a certain number of times. It's got to cross the x-axis a certain number of times, which means it's got to increase and then suddenly decrease to cross the x-axis, then increase again. So what the most helpful tool to get us to, the most helpful tool to get us to accurate values is to find the zeros first, okay? So find zeros, which means set y equal to 0. All right, that's how you find x-intercepts, because the y value is smack dab on the x-axis at 0. So I can factor this, take out an x to the fourth minus 1. Now we talked about imaginary solutions, but in this case we're graphing in the real xy plane. So don't think of this as potential complex imaginary numbers. You can just add the 1, then take the fourth root of it. Don't forget your plus or minus. All right, so we have an x. We have a 0 at 3 different spots. One at x equals 0, one at x equals 1, and one at x equals negative 1. So I'm going to zoom in because it's going to be kind of hard to see really what's going on in between the plus or minus 1. So we have a 0 here, here, and here. The question is, what else is happening to the left here, to the right here, and everything that's going on in between? I'm thinking it's going to look something like this, but I want to be extra sure. So maybe what we can do is go to our calculator, run this through the table, x to the fifth minus x, and I'm going to do my table values I'm going to go for quarters, so 0.25, just to get a more accurate measurement of what's happening in between my zeros. So 0.25 is what my table step is going to be, and then I go to my table. Looks like it's not doing too much in between. It goes to negative 0.75 up to about a half. And And then it comes back down at negative a half to a little bit lower than 1/2. And then at negative 0.25, it's almost exactly 0.25. So what looks like is happening is it's just a slight little bump that's moving up right there. It's symmetrical on the opposite side. So if you go 0.25 out, it's negative 0.25 down. 0.5 out, just a little bit below or above the 0.5. And then if you do 0.75, it's just a little bit more than a half. So it's doing this. So this is the behavior between -1 and 1. Now what's happening beyond that? If I plugged in 2, we're already up to 30. Wow. Okay, so it just shoots up so quickly. And if you plug in -2, it's -30. So it's going way down fast. So there's the graph for number 2. What I really want you to be able to do is not just straight go to the table right away. What I want you to do is show me that you still know how to find the zeros using algebra techniques. Then plot the points in between them. Let's check out number 4 now. Where is my eraser? All right, number 4 has another odd leading power of degree 3. Which, if there's a negative coefficient out front here, what's probably going to happen is you've got a cube that does this. This negative is going to force it opposite this way. Yeah. And now that there's another x term, I'm feeling like this is going to morph to something that looks like that. Because again, the more zeros you create for a graph, the more times it has to change from increasing to decreasing and vice versa. So we're thinking as a prediction, that's what's going to be the case, but we should find the zeros. I can factor an x out. You know what? I'm going to factor a negative x so that my leading coefficient's not negative. It's much easier to factor that way. So take a negative x out. Divide that by negative x, you get x squared. Divide that by negative x, you get -4. Difference of perfect squares, I'm going to just do that right away. X minus 2, x plus 2. Which gives me, excuse me, negative x equals 0, x minus 2 equals 0, and x plus 2 equals 0. Which means divide by -1, add 2, subtract 2. Sorry, I'm getting ahead of myself here. The 3 zeros are going to be x equals 0, x equals 2, and x equals -2. So I'm going to erase this work so that I can just use the graph over here. Just pause it, rewind if you need to see the work again. So here are my zeros. So I don't know if I want to zoom in too far. Let's zoom back a little bit. This is kind of in my face. All right, so 0 is a 0, 2 is a 0, -2 is a 0. By the way, if you're trying to look for patterns, it's not always going to be completely symmetrical like this. It's not always going to be, hey, the zeros are always one of them 0 and 2 of them are going to be plus minus the same number. It doesn't always work that way. If we plug this into a table then to see what the behavior in between is, I'm going to plug in negative x to the third power. Hold on, negative x to the third power plus 4x. I'm going to go by quarters again just to really see what's going on. All right. Let's go. Negative 1.5 is negative 2.6. Negative 1.75 is negative 1.6. Negative 1.25 is negative 3. Okay, it goes further down even past here. At negative 1, it's exactly negative 3. At negative 1.5, it's negative 2.65. Okay, so we're starting to get that symmetry again. Negative 0.75 goes to negative 2.5. Wait, what's this? That's negative 0.5. My bad. Just the ramblings of an aging math teacher. All right, so hopefully you guys are seeing like, okay, this curve, Mr. Owsley's not a perfect point plotter, but you can see how it's moving down, probably zeroing out somewhere down there, and then coming back up again. On the opposite side, we can expect to see a degree of similar, these points corresponding to those points. Go over a half up 1.875, over 1 up 3, 1.25 just a little bit more, 1.5 2.6, 1.75 1.6. I'm sorry. 1, 2, 3. Okay. Got it. I'm okay, people. It's gonna be okay. Okay. All right. Oh, mercy. All right, bottom line is it looks like this. That's what's happening in between the zeros. And here's the deal. After the zeros, for the most part, your behavior is if you are increasing going this way, it's going to continue to increase. And I can easily confirm that by checking negative 3 on the table. Yeah, negative 3 corresponds to 15, so it's shooting up pretty quick. Positive 3 goes to negative 15. So it's moving downward very quickly as well. So yeah, the original estimation for what number 4 was going to be checks out. Let's check out number 6. All right, we've got an even one now. I was wondering when we'd get to those. All right, x to the 4. It is a 3-term polynomial. And it's got that quadratic structure. Remember when the middle term was exactly half of the leading power, and then the last one was a constant? This can be looked at as w squared minus 5w plus 4. And then we can factor it like it's a polynomial of quadratic structure. However, I'm going to take a shortcut here and just say, you know what? This is going to be x squared minus 4 and x squared minus 1. This is how this polynomial would factor down. And then pretty much if you set this thing equal to 0, I could continue factoring, but it's going to create 2 zeros there and 2 zeros here. So x is equal to plus or minus 2 and plus or minus 1. That's really what's going on here. Hopefully you guys can see that better. Looks like it. All right, I want to zoom back in a bit because there's a lot of zeros really close together. So you get a 0, and 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 0 gets a 0. All right, there's 5 zeros for this function alone. Sorry, I'm not sure if the blue's showing up too well here. How's that look? Better? A little bit? All right, so what is the general pattern if it's even? So odd ones kind of had that end loopy behavior to it, although evens tended to have a parabolic type move here. Well, a parabola has got to stop decreasing and come back up, and then decrease again and then come back up, or something weird's got to happen like that. So let's check the table. So if I plug in y equals x to the fourth power minus 5x squared plus 4, what do we get? So let's start. You know what? I'm curious about the end behavior. What's left of negative 2 and right of 2? Just right off the bat. Well, 2.25 is 4. So it's up there. And then 2.5 is 11.8, which is also up there. It seems like it's going really high, really quick when you move in that direction. You know what? I think I got to zoom out. At any rate, it's doing this. And left of 2, same exact thing. All right, what's happening between the lines, between the curves, between the zeros? Well, if I go just right of negative 2, it's going downward. And it seems to be leveling off somewhere around negative 2. I got negative 1.5, negative 2.188. And then when you start looping it back, it's coming up quick. Now, in between negative 1 and 0, negative 0.75 gives me 1.5. Negative 0.5 gives me 2.8. Negative 2.25 gives me 3.69. Yikes. Oh, I'm sorry. Zero's not a 0. I just put it on there randomly. I'm so sorry for that confusion. There's no 0 at x equals 0. If you've been confused for the last 3 or 4 minutes, I deeply apologize. But we're 18 minutes into the video, and I ain't stopping it right now. So, you've forgiven me. All is well. 0, 4, that makes sense. Okay, 0.25, yeah, same as over here. I see symmetry. Yes. Celebrate good symmetry. Come on. There we go. Whoa. Interesting. And then I think we can say that this is going to be replicated over here just with like, hey, that's what we think is going to happen. We will confirm, yes, it's the identical points that move it downward like that. And that's what number 6 looks like. Okay, so this is sort of the main odd power change. This appears to be the main even power change. Okay. So this video is kind of running long. I think I'm just going to stop it, talk about the others in class, and then you guys can determine whether or not you want to see the video on 8 and 10. All right, guys. Thanks for watching.